Good afternoon, everyone. It's my pleasure to introduce today's speaker, Professor Gabriel Mindlin. He earned his PhD in physics from Drexel University, Philadelphia in 1992. Following stints as a professor at the University of Navarra in Spain in 1994 and an associate researcher at the University of California in 2002, he is now a full professor in the Department of Physics at the Faculty of Exact and National Sciences at the University of Buenos Aires, as well as a senior researcher at the National Scientific and Technical Research Council of Argentina, CONICET. He has authored over 150 publications in journals like Nature, Proceedings of the National Academy of Sciences, and Physical Review Letters. He has been awarded numerous accolades, numerous national and international accolades, including the Estimulo Award from the Bunge and Bond Foundation, the Arthur Winfrey Award from ICTP Trieste, and the Connex Award. He is also a fellow of the AAAS and a member of the Latin American Academy of Sciences. He has supervised numerous PhD theses and is also the founder of the Laboratory of Dynamical Systems, where over the years several physicists, neuroscientists, biologists, doctors, and engineers have collaborated to study the science behind vocal learning and birdsong production. He specializes in applying the frameworks of nonlinear dynamics to study the behavior of complex systems. This has led him to investigate problems in behavioral neuroscience, focusing on the study of birdsong. His recent research, which was on reviving the songs of extinct bird species, received extensive attention from National Geographic. Today's talk, titled Listening to a Bird's Dream, Probing Vocal Replay in the Sleeping Brain, promises to be equally exciting. Let's welcome the speaker with a round of applause.
Well, thank you very much, everyone here, for attending the conference. Thank you, Nelima, for the invitation to be here. It's been a pleasure. This is my second time in India, and I love being here, so it's worth every minute of the 26 hours trip from Buenos Aires to here. So what I'm going to be showing you is a result about how we used our studies on the physics of birdsong to sneak into the dreams of a bird and their implications in terms of learning. So I'm going to try to do a summary of what I've been working on for the last 25 or 30 years, because maybe between 25 or 30 years ago, I went to Rockefeller University in New York to give a talk on the nonlinear dynamics aspects of human voice production, and someone in the audience raised a hand and said, well, this has something to do with the way in which birds sing. And I sort of smiled because I didn't know that there were people doing research in birdsong. So this person approached to me later. I answered something using scales. Well, maybe, I don't know, we are 1.8 meters long and we weigh 100 kilograms and our fundamental frequency is 100 hertz. A bird is 18 centimeters long and weighs 18 grams, and maybe the fundamental frequency scales up to 1,000 hertz, so maybe that's okay. So I sort of skipped the question. And then this person approached to me and told me, look, birdsong is a very serious business in neuroscience because it's an animal model to study the problem of how a brain reconfigures itself in order to achieve a very complex behavior, which is vocal communication. So there are 10,000 species of bird. 4,000 of them are called songbirds, are a suborder of the passeriforms. They are ocine birds. They include the cardinal, the canary, the zebra finch, whatever. And they need to be exposed to a tutor in order to learn their vocalizations. So when I learned that, I thought that these neuroscientists were studying the problem of the brain, but they were trying to link every single acoustic feature to one particular pattern of activation in the brain. And I thought that it would be useful in order to complement this program of research to know actually how the bird was generating the song and what kind of physiological instructions they were needing from the brain in order to generate some of the acoustic features. So there started a line of research that lasted the last 25 years, where in principle I had to combine modeling and then set up a lab and measure some of these physiological parameters, and then try to measure, with the help of Anna, who was speaking here yesterday, some of the neural instructions that are generating these instructions that control the song. So lately, I've been using these techniques to study the problem of dreams, and this is basically what I want to describe to you. So, unfortunately, the whole 25 or 30 years of research can be summarized in 10 seconds, in a 10 seconds movie, which is kind of disappointing to me, but we'll do it. A vocal organ called the syrinx, which is a bipartite structure, at least for maybe 4,000 species of birds that are these oscine birds, and they have this pair of labia that are very similar to the human vocal folds. That is, eventually, when the bird wants to sing, it will send a flow of air in between these labia, and they're going to set up some self-sustained oscillations here that's going to modulate the airflow, and the time derivative of the rate of mass injection of air into the trachea is the origin of sound. Then you're going to have waves propagating back and forth, and of course, what the bird can do is, while it's generating these oscillations, it can change the configuration of the syrinx by the use of some muscles and modify the fundamental frequencies of the song. And we're going to be going over the details in a minute. So basically, there is a nonlinear mechanism that is the generation, and then you will be having the signatures of the linear filtering as the waves are traveling back and forth. The labia can be modeled, and this is what I thought at the beginning. The labia could be modeled in terms of the mid-position of the labia, and there is going to be some restitution constant because it's an elastic material, and there is going to be some transfer of energy that we're going to be discussing in a minute because of the airflow and the combination of specific modes in the labia. And that's going to be described as some nonlinear equation, and my idea was that the way in which the oscillations could be set were not arbitrary. We know from normal form theory in nonlinear dynamics that the way in which oscillations can be set up is a finite set of different bifurcations. Each of them is going to give rise of oscillations of specific harmonic contents. So maybe some of the timbre of the song of the bird could be explained in terms of the bifurcations of this system here. This was the general idea that I had in mind. So the first model I proposed many, many years ago had to do with that. Why do you have oscillations? Well, let's assume that you can lose stability in two specific modes. One that is a lateral mode for the labia here, okay? This and this, that are represented by these shapes. So let's assume that you have a lateral mode and that you have a wave-like mode, and that you turn them on in such a way that when the labia are, and therefore a transmission of energy, suggestion constant, you will have some term that takes into account this transfer of energy I was describing before. Sorry, this would be the linear dissipation of the system. This would be the term that I was describing before, which takes into account, which is the average pressure computed, assuming these kinetic modes. And this is going to be the linear dissipation, because when the labia collide with each other or with the walls, they're going to be losing a lot of energy. So in this model, there are two parameters that were crucial, which I thought would be interesting to measure. And the problem is that at the time, no one was measuring that. Or there was just one person in the University of Utah. Since then, we've been collaborating for decades, Franz Goller. That were important for my model. One was the pressure that depends on the activity of the respiratory muscles. And the other one was the tension of this labia, which the bird controls by the activity of this muscle here that is syringealis ventralis. So what the bird does when it's sending this flow of air, so when the pressure is high and you send a high jet in between the labia, is they can eventually modify the activity in this muscle and contract them. If they call, one thing I have to do is to control the phase difference between this pulse of pressure, expiratory pressure, and the tension of this labia, and I can create things that are upwards, okay, or downwards, no? Okay. So this is what I wanted to test, the phase difference between the gestures controlling the restitution constant and the pressure. And in order to do that, I had to learn how to measure these things. Before doing that, let me tell you something else, and this is particularly for the students here. it's always worth it to study a little bit of nonlinear dynamics, and if you have a physical model which has additional parameters, try to convert it into a normal form. Normal form, given some linear singularity that you have, is the nonlinear differential equation that has the minimal number of terms and will be consistent with the dynamics of your problem. So there is a systematic way of doing nonlinear changes of variables into this problem that will allow you to have a minimal set of terms in your vector field. And the reason for which I think it's very important is because there you have really the minimal number of parameters that you have to measure in your problem in order to reproduce the physics. So for example, in this case, you get rid of all the parameters. Here you have only gamma, which is a temporal constant here. But you eliminate many of the parameters, and the only parameters that you're left out with is alpha and beta, which in this case, fortunately, can be associated directly to the pressure and the tension that I was describing before. What I'm displaying here in these diagrams is what in nonlinear dynamics we call a bifurcation diagram. Those are the lines that separate the regions in the parameter space where the dynamics is qualitatively different. So for example, in here you have the pressure, here you have the tension. In all this region that I call 1, you have only one fixed point. Therefore, the labia are quiet, okay? And you have to increase beyond certain value the pressure in order to undergo what is called a bifurcation, a qualitative change in the dynamics. In this case, is what is called a Hof bifurcation that gives rise to oscillations of the labia, oscillations that are born in this region here. The whole bifurcation diagram is not of interest in this talk because it's kind of technical, but what is important is that the normal form will have the same kind of bifurcations, and therefore you can study the normal form, which is a much simpler differential equation with less parameters, and therefore easier to study mathematically.
Could you explain what is x and y are in terms of the bird?
So in this case, x and y correspond to the midpoint position of the labia and the derivative, because what I'm setting here is Newton's equations for the midpoint position of the labia. So it will be the derivative and the derivative of the velocity, the forces. And the forces will be these forces because of the average pressure, the dissipation, the nonlinear dissipation, the linear dissipation, the restitution constant. And in here, wherever it comes out of doing the normal form. So in here you have a clear interpretation. The price that you pay when you do normal form is that maybe what you have is more difficult to interpret.
Where's the time dependence in the first set of equations which you have?
Exactly. Well, we'll go.
No, the first set, I don't see the. Is it through the pressure?
So it is through the pressure and eventually through the K. Also through K. So in both cases here, they will have time-dependent parameters, and in here I write them explicitly. Some other question? Okay, let's continue. So how realistic is the kind of sounds that you will get if you synthesize a song with a normal form? So what I'm going to show you here is a recorded song of a zebra finch. Let's hear how it sounds. That's it. This bird has to learn the vocalization, but this is the only thing that will do. Less than 2 seconds of sound, and it will repeat it over and over all its life, practicing all day long. And when it sees the female, will look very attentive to her and sing it over and over like a machine gun, you know, with a huge precision. Now, what I'm showing you here is once that you put a time dependent for K and beta and simulate the sounds, that means you integrate for X, simulate for the sound, filter it properly, and so on. This is what you get with a normal form. That means with a super simplified two-dimensional dynamical system. Okay, so we're very happy when we found this because you say, well, this sounds kind of like a zebra finch. Let's see what the bird thinks. And our first test for this was something that we did together with Anna several years ago, where we did the following experiment. We exposed a sleeping bird to its own song. And in HVC, in a nucleus, and part of the brain of the bird that is responsible for generating these instructions, when the bird is sleeping, if he hears the same song that he sang during the day, although he's completely asleep, the same neurons that were participating in the generation of the song will get activated when it hears the recording. Okay? So what I'm showing you here is 60 repetitions of an experiment, and in each repetition I'm going to be playing the song, and as you see, every one of the times you get a specific response in here. If you add them all together, you see this systematic increase in the activity in some particular temporal instances. That happens if you play the Birdsong song, okay? If you play the same song backwards, then you have nothing. So it doesn't have to do with specific notes, because if you change the order, you have no response at all, okay? If you play the song of a conspecific bird, that means another zebra finch that lives in the other cage just by it, and you play that song, there is also no response at all. Okay. I'm going to show you the end of the happy story. The truth is that when we did the experiment with quality very similar to what we had before, we played the song and we had no response at all. It was very dramatic because I was claiming that the low-dimensional model was good and the bird couldn't care less about that. We had to tune some parameters, we had to put the linear filters properly tuned, and eventually we managed to cheat the bird into thinking that the synthetic song was the real song. And for many years, what I've been doing is different experiments to try to show the pertinence of this kind of stimuli on birds. So we've done it with laboratory experiments, we've done it in the field, we've trained juveniles, we've tried to cheat, use the model to see what is sexy or not, or intimidating in a song. So that's one of the applications that we have for the model. But what is pertinent to this talk is that we also had to develop some techniques together with Franz, my friend Franz Gehler. He was a wonderful surgeon of birds, and he trained us to do the surgeries, and we paid by designing some electronics on this. So this is typically the kind of measurements that we take. On one hand, we insert a cannula into the thoracic air sacs, and we send the other end of the cannula to a pressure transducer, and we measure the air sac in the bird while the bird is singing. And we also do a surgery where we insert microelectrodes into these muscles, and we send the electrodes under the skin towards an amplifier that is here. So when the bird undergoes this anesthesia, wakes up and starts to sing to the female. These are very delicate surgeries to do because the bird has to be in good mode when it wakes up in order to start to sing, because the electrodes won't be in their position for a long time. So the kind of measurements that we took had into account this idea that if I put these temporal parameters into the model, I should generate realistic sounds. And this is basically what we did for a long time, trying to study, by the way, the different features of these gestures in particular. But what is pertinent for this talk is that they allowed us to start to study quantitatively the sleeping brain, the bird's brain, well, the brain of a sleeping bird. How does it go? In the year 2000, one of our closest collaborators, Dan Margolias from the University of Chicago, he did these experiments which I thought were very interesting, that consisted in recording during the day what some neurons in a specific nuclei of the song system, RA in this case, when they were spiking while the bird was singing. So this is the activity in a nucleus called the robustus algestratum in the song system, part of the neural nuclei that the bird has in order to sing, when the bird is singing. And in some specific times, there's going to be spiking. Interesting enough, what Dan found is that when the bird would be sleeping, spontaneously, you will have some neural activity recorded when the bird sleeps. And in many instances, what you have is a temporal pattern that is very similar, extremely similar to what the bird was using when the bird was singing. So, if there is a specific pattern that is associated to the production, what he found is that during sleep, eventually the same pattern could be registered. Yeah.
Not induced.
Exactly. In this case, it's spontaneous. Exactly. We'll see what happens if we try to induce it. But in this case, it's spontaneous. The bird is sleeping, is not waking up, and suddenly, from time to time, you have this replace of activity in the same regions where the neurons were active with the same pattern when it was singing. Exactly. Yes. So the measurements are made with electrodes of very high impedance, and therefore what you have in here is single neuron recordings. So you go with a high impedance electrode close to a neuron, and then you wait until it sings. And you're recording here the extracellular activity close to one particular neuron. Yeah. What was very interesting is that from time to time, you could also see patterns that were not that similar to the ones that were used during the song production. And the problem here is that you don't know how to interpret, right? Because we don't have the coding for the brain of a bird or the brain of almost anything. So we see a pattern of activity, and in principle, it's very difficult to associate it to behavior. So there were also spontaneous replays that were different from this, and it was very difficult to interpret those. So this was challenging, and this line of research sort of like slept for a few years. And in the meantime, as I was telling you before, we were interested in something else at the other end of the sound system, trying to measure the air sac pressure during sound production and the activity of muscles. This is syringealis dorsalis, and this is VTB. So here we have the bird singing two motifs. These are two identical motifs, and if you pay attention to, I don't know, the pressure pattern that is used to generate these notes that you have in this syllable in here, when it repeats it, you're going to have the same pattern of activity in the pressure. And the same would happen with the tension, and everything is quite systematic, modulus the variability that you have in biology. So far, these are two different programs of research, until by chance, we left one bird connected during the night. And this was really shocking to us, because what we found is that in the syringeal muscles, while the bird was quietly sleeping, this is the normal respiration of a quiet, the quiet respiration of a sleeping bird, from time to time you would have these patterns of activity in the muscles that strongly resemble the segments that you would measure during the day when the bird was singing. So this replay that would happen in the brain didn't affect the respiration, but they did affect the muscles, okay? See, reproduce the shapes that were used during some production. So this is a typical recording. It's very boring. You are finding the correlation between this infinite time series of hours of recording with these 10, 20 milliseconds patterns of activity. And just from time to time, you have these peaks where you have high correlation of all this pattern with one specific pattern used in some production and another one there.
Does the bird actually make a sound?
No. It's completely silent. Okay, it's completely silent. So you have, in order to generate sound, you have to not only control the syringeal muscles, but you have to send these jets of air in between the labia. That part is the part that is inhibited. So the bird is with its eyes closed and having a 2 or 3 hertz respiratory rhythm that has nothing to do with the very rapid production of pulses that you have during some production. Okay? So it's completely silent. Instead of having these huge pulses of pressure fluctuations that allow you to set up a jet in between the labia, you are having these very regular oscillations that correspond to a normal breathing. Okay? But you have these patterns of very rapid activation that are similar to this. Okay? So let's see a dream, what I call a dream, a night of sleeping of the bird. So at the beginning, the bird is practicing basically all the syllables, and you see all these events. What I'm calling an event, one of these instances where you find a high correlation, okay, with the pattern that you have previously, and you count the number of events. So maybe during the first hour, you have practices of all the patterns. But then it's very interesting because 1 hour later, it might be practicing a lot, just the blue pattern in there. And maybe the next hour is going to be practicing again, just the blue pattern in there. And maybe the next hour is going to be practicing the red pattern several times during that hour. And then some combinations and so on. And at the last hour of the sleeping process, it will practice the whole song. The whole song is going to be practiced only at the end of the night. And this is one bird, one night, but this is very systematic. And this is something that we did with France in 2017. Here you can have some histogram of the kind of practices that you would have. Some syllables are going to be practiced more, then some combinations, then some longer combinations, and the longest ones which are practiced just a few times. So one thing that we did for fun, and I like sharing, is the following. You will have, so let's really imagine what's going on. This is what we have for one particular bird that is singing systematically a repetition of motifs. So the zebra finch learns the song, but it learns one stereotype song and will repeat it over and over. So here it is what it sounds like, that song. I'm going to play it again because I want you to imagine what is our lab like. It is maybe 10 of these birds singing all the time this one song over and over. It kind of drives you crazy. So it's all it does, right? It practices this one song. But then what I did is, well, let us take these instances where the bird is replaying at night, silently, some specific patterns that I can identify. So let's find the sounds of these segments, and let's listen to bird's dream, okay? So what I'm showing you here is a composition of some segments whose script corresponds to the muscle activity that was used to generate that during the day. Okay? So this is what the bird sounds like in its dreams. So this is what the bird is dreaming. This is what I call. So I like it a lot because beyond statistics, this is what the sound associated to practice is like for a sleeping bird. What is very interesting to me is that notice that here you have a very stereotyped repetition of syllables, and here you change it completely. For example, here you have this repeated twice, this, you repeat this again, with a different rhythm, so all the stereotypy is broken completely. It's doing a much more crazy stuff.
So how do you know the dream sounds like that? Because the respiration pattern is not working.
Exactly. No, this is what the sounds would correspond to the tension that I measure. So this is the correlation. In principle, in order to synthesize the sound, I have to turn the oscillations on. So in order to, if I want to synthesize it, and I'm going to show that in a minute, I would have to imagine some pressure fluctuation, okay, and conjecture some pressure fluctuation. We're going to go in a minute, but this is not a synthesis. This is just cut and paste sounds that correspond to the specific tension patterns that I measured.
Correlate with what it does when it is awake.
Exactly.
Okay.
So when it's awake, to every specific tension pattern, I have a sound. So here what I'm doing is I detect it at night, I cut and paste a little segment. We'll go into the problem of synthesis in just a minute, in a few minutes.
Since you used the term improvement during the training session, is there an improvement in learning? So is there an improvement in the bird song itself, like before and after?
Well, let's leave that for the questions. I promise I will answer this question, although it will start with I don't know, but I promise I will answer and elaborate on that. But it's a key question. A little bit of statistics. You would have syllables plus unknowns, 2 syllables or more, incorrect timing, partial syllable, complete motifs. Only 6% of the times the bird is doing the complete replay, which for me it's very exciting because during the day it will only do stereotype things. During the sleep, the replays only 6% of the time are going to be the systematic replays. So what can we do with this? Let's think of this now as a tool. Can we manipulate dreams? Can we override dreams? A little bit what you were asking before. What if we could actually listen to them? What happens if you listen to your own dreams? It's kind of experiments you can start to play doing. So let's see what we can do in that regard. So what I was describing before is this experiment where what you do is you expose a bird to its own song, to a reverse song, to a conspecific song, and to a synthetic copy. I'm saying now that I can measure activity of spontaneous activity in the muscles. Can I induce these patterns in the muscles by exposing the birds to songs, synthetic or not? So we'll do the version of this experiment now. What I'm measuring now is the muscle activity of a singing pattern, so with all its acoustic features in here. And what I'm doing here is taking a sleeping bird, exposing it to some copy. In this case, it's exactly the Birdsong song, and I'm measuring the elicited pattern. And what I do here is I superimpose the result of several experiments, and as you can see, you have a pattern that is very similar to the pattern that was used during the day. It's not exactly the same, right? So sometimes you don't elicit responses, so it's not 100% that you have an effective elicitation, but you do elicit patterns of activity very similar to the Birdsong song. So what happens if we try to reproduce the same thing? Here I'm showing you the Birdsong song, and that means the muscle activity measured in the syringeal muscles of a bird that is exposed to the Birdsong song. I'm showing you what happens if you play the reverse song, which is absolutely nothing. Now what happens if you expose the bird to the conspecific, and again, this is nothing. And if you play the synthetic copy, you have a pattern that is pretty decent. Pretty decent. Of course, it is not as precise as what happens if you expose the bird to its own song, but it's pretty decent. You recognize the shapes that when you elicit the patterns are the right patterns. Of course, what we can do now is some experiments manipulating the synthesis. In this case, it's a very conservative experiment where what I do is expose the bird to different segments of the song. So it's the same song minus a few syllables. So for example, this is a song, A, B, C, D, and this is what happens if you elicit, what kind of response you get if you send as a stimulus the whole song minus syllable A. And it's only at the end that you start to have responses. What if you send A, B, C, D minus B, so A, C, and D, and you have this pattern of activity, etc. This is something I'm not going to be discussing today. But this is something that I liked a lot. It is what you elicit when you start to degrade the stimulus. So you have a synthetic song, and you can play with the parameters. And you can change the parameters here. You can change the noise that you put for the muscles. You can change the amplitudes of the parameters. You can change many features. How you degrade this. And it's interesting that what you do is that you degrade by making some segments appear less frequently. That means that you don't degrade the response gradually, but what you do is that some segments are elicited less frequency. When they are elicited with the right shape, but they might be elicited less frequently. Okay? So here's the effect of, for example, changing the level of noise in the parameters, which is a parameter that's important in here. And this is the kind of percentage of responses that you get. And suddenly you have a big decrease in the responses that you get. Now, can we induce a dream? This is a question that you asked me a little while ago. So what I'm measuring here is the dream of a canary, which has these stereotyped syllables. And whenever I find that that the bird is replaying this song, what I'm going to be doing is playing the Birdsong song. So now what I do is I expose this bird to a copy of the song. And what happens in here is that the bird basically interrupts this spontaneous activity and starts to display the pattern of activity that would be associated to that sound. So you induce a dream or a replay in the brain of a bird just by seeing when it is in a stage where it's showing these displays and replacing the spontaneous activity with something that you control. Behaviorally, that was very interesting to me because I want to know which is the effect, well, a little bit what you were asking before, what is the effect of having these spontaneous irregular replays? If instead of having crazy dreams or crazy replays, if you would have stereotyped replays, what would happen behaviorally? So this is a tool to do it. But in any case, another important thing is whether this is related to learning or not. So this is the set of species of birds. There are like 29 orders of birds, but this order, Passeriformes, which is the blue and the red, accounts for half of the bird species. Okay? These are the sign birds, the birds that learn, and these are the sabocines. Those are phylogenetically close, but they don't need to learn. They will have their song imprinted in their genes. My question was, do you have replays and dreams in the birds that don't learn? So in order to do that, we had to open a line of research that involved working with wild birds. And this is a kiskadee. This is Pitangus sulphuratus, which is a sabocine that lives in Argentina. Working with wild birds is another business altogether. You have to get very special permits, run very precise experiments, return the birds to the wild, and so on. And the way in which they manage their physical organ is completely different than ocine birds. And this is an interesting aspect. You have 10,000 species. Ocine birds do things similarly, but then for every other order or suborder, you have different ways of managing your vocal apparatus. So I don't know if you, well, many of you are very young, and many of you look like you could have very young kids. So I don't know if you notice what happens with teenagers. I don't know if it happens here in India, but in Argentina it happens for sure, that a teenager can spend, I don't know, 2 hours in front of the mirror to try to look kind of mean, no? Intimidating, right? It's going to do something with the hair and the earrings or whatever, break the pants, whatever, so just to look mean. Well, kiskadees do something very similar with their song. So they modulate the frequency. The frequency modulation is done by the pressure gestures, but they will use muscle activity to have the two sound sources slightly out of tune, and they control by sending some stereotyped signal. They will force the two sound sources to be slightly out of tune, so this sounds rougher, okay? So here are two sound sources simultaneously active, relatively different frequencies, and therefore the sounds like, okay, kind of ugly, intimidating. For some reason, they also like here to put a touch of roughness. And all kiskadees all over the world will do exactly the same things, genetically programmed. They don't learn this. So you have very specific patterns of activity. I wanted to know whether you could have replays of that in sleeping birds, and the answer is that you do. You have these patterns of activity. The only thing is, instead of being at 180 hertz, which is the frequency difference at which they will be modulating the song, is slightly lower. And also they are going to be slightly larger. So the duration is going to be larger in principle. So here you have the sound, the spectrogram, the EMGs that you have. This is the EMG activity that you measure, and this is the modulation of the sound that you get, giving rise to this roughness in the sound. completely correlated the frequency modulation with the EMG frequency. Actually, from the point of view of nonlinear dynamics, forcing a system with a frequency difference of two sound sources to couple them is kind of a sophisticated thing to do. But anyways, this is what they do. The muscles are different. This is obliquus ventralis muscle, but it's more or less similar to the syringealis ventralis. And you can write a model for the two sound sources here. And now this EMG will enter into the restitution constant for each of these two sound sources. So when you integrate these differential equations and you synthesize the sound, you can have, which is the sound of the syllables and the sound that you would get if the pressure is assumed to be the same that you would have when it's singing, but with the right frequency modulation. So this is the typical call of the kiskadee. And this is the synthesis that you get, okay? Which is kind of very similar. But you don't have only that vocalization. When these birds have this replay in the muscles, they also have some interesting thing. Okay, what I showed you was the typical call of the kiskadee. It has another vocalization. It is a trill that they do when they get very upset. And let me show you what they do when they get upset. So there was a little trill there that happens at the same time that the bird is displaying these feathers that are coming out. So the student, the grad student that was working on this one day told me, well, I could measure the trill. So the bird does the replay of the trill. When the bird is sleeping, you can measure from time to time the replay of the trill. And I said, well, did you make sure that it was sleeping? It has the eyes closed and so on. So we went to see the movie, and this is what we found. The bird was silently sleeping, but then it would have this very display in here. So now let's look at both together, the muscle measurements and the movie. Okay. You see, when you have the appearance of this replaying here, it will also have these feathers coming up. That's the reason I told Juan, you've been the first person to record a nightmare in a bird. So here's the replay. This is the synthesis of sound that will be associated to that replay of activity. And now let's see the final aspect. What would happen if we try to do with no sign birds the synthesis of sounds driven by the EMG activity. So I'm going to describe work in progress. What we're going to be doing now is taking these EMGs, we're going to be inserting them into the model of voice production, assuming some pressure whenever you have patterns of activity of EMG and synthesized sounds, but for sign birds, not for sabocines. If you do that, this is what you get. This is the sound of the bird. These are the measured gestures. That means measuring the EMGs, the pressure, the expiratory EMGs, and so on. And this is the synthesis that you get. And this is for a singing bird. And what you find is that it's reasonably fine. So the model does capture many of the acoustic features. We're still tuning it up. The idea now is to use this model to generate this only with the EMG data. We need that in order to do experiments with sign birds and modifying parameters to try to see which is the impact in learning birds to the sound of their dreams. But this is work that will be done, but it is being done right now. So I'm going to describe it in my next visit to Chennai, probably. This is what we're working on now. So what we plan to do is to extend this synthesis that we did for sabocines to sign birds, expose a sleeping bird to the synthesis of its dream, and trigger the Birdsong song when a sleeping bird starts to dream. That means avoiding spontaneous replays and inducing stereotype dreams. What would happen if you are not let have crazy dreams? What would happen if you are exposed to have systematic dreams? Okay? These are the kind of questions that we're trying to address. And as I was telling you before, we'll see what happens with that. So in conclusion, the periphery, to me, is very important, and you cannot do neuroscience without thinking about the body. Neuroscience usually thinks that everything happens in the brain, and we are integrated. We are the union of a body and neural activity and an environment, and behavior emerges of the interaction of the three. And many of the acoustic features are determined by the biomechanics. You don't have to look for where it's coded, because it's not coded anywhere. It emerges out of the dynamics of the vocal organ. So I think that behavior has to be looked at in an integrated way where physics has to play an important role. Besides this idea that I've supported by showing you that with very simple instructions with the right bifurcations, you elicit things with a timbre that is the right one, you can also use the periphery as a window to study the central nervous system. In a way, now we have an operational way to read replays. And I use dreams because I'm a physicist and I don't care about what biology say. Probably you don't have to use the word dreams, but I use dreams as a synonymous of replay because it's much more fun. And we're collecting questions, like, for example, non-learning birds. Do they practice outside the stereotypy? And the answer seems to be no. It seems to be that the birds that don't learn replay very silly things. None of the crazy things that the learning birds do need to have. We've done this with only one subocene species. There are 10,000, I know. But it looks like, birds that don't learn have more stereotyped dreams as well. What if we induce stereotyped dreams? I think that this is going to be very interesting. I think that it's very important that you practice these crazy things. I don't know if for some brain consolidation process or for muscle activity and practice, we still don't know, but it's going to be very interesting to know what would happen if you don't let a bird have crazy dreams, but you induce stereotyped dreams. And what if we let the birds listen to what they dream? Is there a reason for we practicing crazy things, or I'm talking like me if I was a bird, for a bird practicing a crazy thing, what would happen if I would listen to that replay? So this is something that we're working on, and we're very excited about what we can learn from there. So let me finish my presentation by acknowledging my co-workers. For example, most than anyone, Anna, together for 30 years now, and has become a master and a friend as well. And then Margolies from the University of Chicago, whose work with Anna she described yesterday. Juan Dople is the grad student that measured subocene work, and he worked 5 years with a species no one had worked before, had to do field work, had to capture birds, had to model the physics of birdsong production for that one species, measure the dreams of them. It was an intensive a biologist who allowed us to sex the birds in the field and stuff like that. And these are other grad students involved in different projects we didn't have the chance to share with you today. And with that, I thank you for your attention.
Are there any questions? For the learning and non-learning birds, do the results change based on the age of the bird?
Can you repeat it?
Do your results change depending on the age of the bird?
Okay. So that's an interesting question. The answer is that we are only working with adults because many of these surgeries, I cannot do them on juveniles. When you try to do any of these measurements in a juvenile, what the bird will do is it will stop singing. So many of these questions, which, as you suggest, will be very important to do developmentally, I cannot do them because I cannot measure them. So all what I've shown is adults, and I'm looking forward to better experimentalists to be able to do this with juveniles. I could never succeed.
It's a follow-up to that question. So it's very intriguing to learn that they don't learn to sing at all if you do the operation when they're juvenile. So you think it does something to the learning circuits?
No, it's not that they don't. It's not that they don't learn. They get inhibited and they don't sing. So if you take a juvenile during this process of learning and you do the surgery, then what will happen is that for a few days it won't sing. And for example, for some of the surgeries, like the ones in muscle in particular, after a few days, you lose the electrodes. So the electrodes are lost before they start to sing again. So they will learn normally, but there are a few days where they stay quiet. Yeah.
So do you find a reason as to why they do these learning things? And more importantly, did you explore other species or other, again, like maybe some cats or dogs probably, as to whether they do this?
If you would know how many years it takes me to stay, just to learn a little bit of one species. And someone would ask you this question. Thank you for the question. No, I haven't started. I'm having a hard trouble just when I jump from zebra finches to another species. Now it takes me like 5 years of work. So I have a biologist who is one very good friend. He's a wonderful ornithologist. And from time to time he comes to my lab with this innocent face and says like, have you heard this particular bird? And I know that whenever he says that, I'm going to be like 5 years working on that. And it's like, wow, just 5 years, just wasted, just for one question of one species. And these are just birds within close families. So the answer is no, but it would be very interesting to know which of these mechanisms are also present in other species so distant.
And did you know why do they do this learning things? What is the reason?
Well, this is very interesting because there is no indication whatsoever that learning has an advantage in terms of evolution. Right? So you have many successful species that don't learn. And actually 60% of the species have done it wonderfully in the same environment without learning. So learning appears simultaneously 3 times in the evolution of birds. In this suborder, the suborder of assigned birds in the passeriforms, then the order of the hummingbirds and the parrots. And those are 3 independent solutions with different neural structures, very different architectures in these 3 orders. And we don't know why it appears from time to time evolutionary or what advantage they would give them. What we do know is that in some species, learning has an effect that is contrary to what learning is for another species. For example, there are some species where the female likes the song of a guy who sings like that. And in that case, the action of learning is to focus in endogamy. But there are other species where the females like songs that don't sound like that. So in those cases, learning has the contrary effect. So it's a very confusing, typically biologically complex situation where the same mutation, the appearance of learning, has in different species different effects. Very complex problem. The answer, we don't know.
My question's about the model you introduced in the beginning regarding the syringe, where we took the model involving the force equation and converted that to a normal form. So 2 parameters, that is pressure and the force constant K, are mapped onto alpha and beta, right?
Right.
So to what extent does converting to the normal form actually reproduce the results that the actual equation would? And is there a specific region in the alpha beta plane that sort of corresponds to all this? And also, like how exactly is pressure and P and K mapped to alpha and beta? Are they like monotonically increasing functions of each of these? Or?
Well, thank you for the question. So alpha and beta, just by chance, are a simple nonlinear function, alpha of the pressure and beta of the tension. And there is no reason for which you wouldn't have an arbitrary rotation and a very complex nonlinear function. This, just by chance, turned out to be alpha and beta. So,
and they're monotonically increasing.
And it's monotonically increasing. In terms of what they give you, in terms of results, and what they use of the normal form, this is very interesting. And this is something that I would like to do, and I don't have time to do it, and I'm closer to retirement now, and I know I won't be able to do it, but I would love to do it. Is the following. For example, a canary will work only in this region of parameter space, because you will just be generating tonal sounds, and tonal sounds are sounds that are being produced when you turn the oscillation on with the Hof bifurcation. That is, the amplitude grows from 0 at a very well-defined frequency, and you have kind of bounded harmonic content. But vocalizations of zebra finches, for example, alternate. They will have some tonal sounds that are generated in here and some rough sounds like harmonic stacks that are generated in here. So when you have a saddle node in a limit cycle bifurcation, what you have is that in phase space, what you would have is that the labia are quiet because they are in an attractor in here, but when the oscillations start, it's because this saddle and this node collide, and the stable manifold, which was the stable manifold of the node, become the periodic solution. But it's a periodic solution with a critical slowing down. That means that here, since you had two fixed points, here you are going very slowly. So what you have is sort of like explosive oscillations. Therefore, the harmonic content of this signal is very high. So for example, zebra finches generate in this region of phase space the vocalizations. My conjecture is that you can place every bird species when you take the proper time constant of normalization of the vocalizations into account into a set of oscillations that can be mapped into a unique bifurcation diagram. I would love to do that work, and it's a lot of work, a lot of compiling a lot of songs, but what I have is just a few species. Tonal sounds are generated in Hof bifurcations, rougher sounds are generated in here, and I expect that for simple systems where you don't have two sound sources simultaneously active and so on, you can place them and fill this bifurcation diagram. I would love to do that work.
Also, just one last question. What exactly is the purpose of approximating around the fixed point? Is that a certain...
Yeah, right. Yeah, because basically what my idea is that turning the oscillations on is going from being at a fixed point that is an attractor, that is the two labia that are quiet, into going in an oscillating regime. So in order to have, so you have your parameter space, let's say the pressure, you have the tension here, and you have a region of oscillations in here. So singing, producing a C level, let's say that I have a C level that is like this, is entering this region and exiting at the region of a higher tension. So in that case, you start your oscillations in here at the low frequency. While you are in the oscillating regime, you are increasing the tension, and you turn the oscillations off at a different frequency. So what I need to find is the bifurcations of these fixed points, that is the labia being quiet. Turning them on is starting the oscillations. Turning them off is quitting the oscillation. So I know that I have a fixed point that has to lose stability. My problem is, do I lose it in a Hof or in a saddle node in a limit cycle? Therefore, I have a codimension 2 problem. The normal form of that is something with 2 zero eigenvalues, and therefore, my normal form is going to be the one that corresponds to a matrix that has 2 zero eigenvalues degenerate, so I can study at the same time what leads to a Hof bifurcation or to a saddle node in a limit cycle. Now I know that I have to have at least 3 fixed points, so I'm going to be going to the cubic order. Okay? And this is the rationale for this. My only freedom here is the sign of these terms. There is only one that will give me something that is compatible with what I have in here. And that was the whole logic of it. To be close to tonal sounds or rough sounds, therefore saddle node or Hof, therefore a singular value for the oscillations, for the bifurcations of that fixed point with 2 zero eigenvalues. And then the normal form from there.
I'd like to invite our FLD to present the speaker with a memento.
Oh, thank you very much. Thank you very much for all your hospitality during this visit. It has been wonderful to talk to you people, and if you want to chat or ask any other questions, we'll be around, and it has been a real pleasure and a real treat to be here these days. So thank you very much.